Hello, and welcome to my channel, ForMeVu. This video is the second video of the CCNA course, and, still we're an introduction to network. This video is very important if you want to pass the CCNA certificate or if you want to move forward, and to improve your networking level. Before starting, welcome for the people who have just subscribed to my YouTube channel, and thank you for the likes and comments. If you want me to put another video in French language or Arab language, leave a comment. And, if this is your first time watching my videos, and you haven't subscribed to my channel yet, please to subscribe, and don't forget to leave a like and comment, to publish other videos. Okay, in this video, I will compare TCP/IP model with OSI model, and I will explain physical layer with depth detail. Further, I will explain and compare cabling type, and exactly UTP cable and fiber, okay? As I said in the first video, on the 1980s the International Organization for Standardization, ISO, created Open, Vendor-Neutral Networking Model Open Systems Interconnection, OSI, to aid competition and reduce complexity. The OSI model has many similarities to the TCP/IP model which I detailed on the first video. First, the OSI layers each refer to multiple protocols and standards that implement the functions specified by each layer. OSI committees did not create new protocols or standards, but instead referenced other protocols that were already defined. For example, the IEEE defines Ethernet standards, so the OSI committees did not waste time specifying a new type of Ethernet, it simply referred to the IEEE Ethernet standards. You should know that, now we use the TCP/IP model and not OSI model. The OSI no longer exists as a networking model that could be used now, instead TCP/IP model. For the CCNA, you need to know some information about OSI model. OSI breaks the application layer intro session, presentation, and application layers. This picture compares the 7-layer OSI model with both the 4-layer and 5-layer TCP/IP models. Even though the world uses TCP/IP today rather than OSI, we tend to use the numbering from the OSI layer. For instance, when referring to an application layer protocol in a TCP/IP network, the world still refers to the protocol as a Layer 7 protocol. Session layer is responsible to establish, maintain and closing session identified by their port. Presentation layer is also known as translation layer, and the main responsibility of this layer is to provide or define the data format and encryption. Application layer, like I said on the first video, the application layer does not define the application itself, but it defines services that applications need. If you have not yet understood the application layer and the other layer, I advise you to watch the first video, you will find examples for ease of understanding. Finally, you should know that OSI uses a more generic term to refer to messages, rather than frame, packet, and segment. OSI uses the term Protocol Data Unit, PDU. OSI simply refers to the layer X PDU, LX PDU, with X referring to the number of the layer being discussed. So, I explained the TCP/IP model and the OSI model, now I start to explain the physical layer on deep detail. Don't forget to bring your notebook and note because the rest of this video is very important in CCNA. Okay, first let me remember you what does mean the term Ethernet. The Ethernet refers to an entire family of standards. Some standards define the specifics of how to send data over a particular type of cabling, and at a particular speed. Other standards define protocols, or rules, that the Ethernet nodes must follow to be a part of an Ethernet LAN. All these Ethernet standards come from the IEEE and include the number 802.3 as the beginning part of the standard name. In Part 1 of CCNA, I will explain this category in green because it focuses on physical layer and cabling. Whereas Part 2 in the next video I will explain the other category because it concerns Layer 2 of the TCP/IP model. Okay? Today, Ethernet includes different types of optical and copper cabling, and for speeds of 10 megabits per second up to 400 gigabits per second. There are UTP cables, which is used to transmit data on electrical circuits via the copper wires inside the cable, And there are fiber optic cables that allow Ethernet nodes to send light over glass fibers to the center of the cable. Usually are used for long distances. The IEEE defines Ethernet physical layer standards using a few naming conventions. The official name begins with 802.3 followed by the speed, as well as a clue as to whether the cabling is UTP, with the suffix that includes T, or fiber, with the suffix that includes X. Here is a table which shows the different examples of the types of Ethernet. So we have 10 base T or Ethernet, and we have 100 base T or fast Ethernet, and we have 1000 base T or Gig Ethernet. For example, we find the standard 802.3U which supports 100 megabit per second, and therefore it is fast Ethernet or 10 base T. On CCNA, you should memorize these standards and the speed of each standard. Let's analyze and understand physical links between any two Ethernet nodes, and first, specifically those that use unshielded twisted pair, UTP, cabling. The cable UTP holds some copper wires, grouped as twisted pairs. The 10 base T and 100 base T standards require 2 pairs of wires, while the 1000 base T standard requires 4 pairs. Each pairs of wire should be twisted to limit sensitivity to interference and crosstalk in cables. Each wire has a color-coded plastic coating, with the wires in a pair having a color scheme. For example, for the blue wire pair, one wire's coating is all blue, while the other wire's coating is blue and white striped. You don't need to memorize colors for CCNA. So, while it is true that Ethernet sends data over UTP cables, the physical means to send the data uses electricity that flows over the wires inside the UTP cable. To make that work, the electrical circuit requires a complete loop between wire. And, to send data, the two devices follow some rules called an encoding scheme. So, the transmitting node changes the electrical signal over time, while the other node, the receiver, using the same rules, interprets those changes as either zeros or ones. And, many Ethernet UTP cables use an RJ45 connector on both ends. The RJ45 connector has 8 physical locations into which the 8 wires and the cable can be inserted, called pin positions, or simply pins. Now, I will explain some important rules for Ethernet cabling, specifically for 10 base T and the 100 base T, and 1000 base T. Let's begin with 10 base T and the 100 base T, because both use UTP cabling in similar ways. The 10 base T and 100 base T use 2 pairs of wires in the UTP cable, one for each direction. That means, one wire is used for transmission, and the other wire is used for reception, okay? To better understand, imagine that we want to connect PC to some devices work on layer 2, like a switch or hub. I will explain these devices on next video with deep detail. So, imagine that PC is connecting to switch or hub using 10 base T cable or 100 base T cable. Image that the PC is on the left and the switch or hub is on the right, okay? So, the transmitter on the PC on the left must know the pin positions of the 2 wires it should use to transmit. Those 2 wires must be connected to the correct receiver pins in the RJ45 connector on the switch. To understand the wiring of the cable, which wires need to be in which pin positions on both ends of the cable, you need to first understand how the NICs and switches work. As a rule, Ethernet NIC transmitters use a pair connected to pins 1 and 2. The NIC receivers use a pair of wires at pin positions 3 and 6. LAN switches, knowing those facts about what Ethernet NICs do the opposite. The receivers use a wire pair at pins 1 and 2, and their transmitters use a wire pair at pins 3 and 6. To allow a PC NIC to communicate with the switch, the UTP cable must also use a straight-through cable pinout. An Ethernet straight-through cable connects the wire at pin 1 on one end of the cable to pin 1 at the other end of the cable. The wire at pin 2 needs to connect to pin 2 on the other end of the cable. Pin 3 on one end connects to pin 3 on the other, and so on, as seen in the picture. A straight-through cable works correctly when the nodes use opposite pairs for transmitting data. Okay? However, when two like devices connect to an Ethernet link, for example, a communication between two switches or between two hubs, so they both transmit on the same pins. In that case, you then need another type of cabling pinout called a crossover cable. The crossover cable crosses the pair at the transmit pins on each device to the receive pins on the opposite device. This concept is much clearer with this figure, shows what happens on a link between two switches. The two switches both transmit on the pair at pins 3 and 6, and they both receive on a pair at pins 1 and 2. So, the cable must connect a pair at pins 3 and 6 on each side to pins 1 and 2 on the other side. Okay. For CCNA, you should remember that the 10 base T and 100 base T use two pairs of wires in the UTP cable, one for each direction. And you should know the difference between crossover cable and straight-through cable. So, crossover cable, if the endpoints transmit on the same pin pair, for instance if the endpoints are both switches or both endpoints are PC. Whereas, straight-through cable is used if the endpoints transmit on different pin pairs. Okay? I give you a little break, and we continue. Now I will explain 1000 base T. 1000 base T or gigabit Ethernet requires 4 wire pairs, and it uses more advanced electronics that allow both ends to transmit and receive simultaneously on each wire pair. So, the straight-through cable for 1000 base T uses the 4 wire pairs to create 4 circuits. It uses the same pinouts for 2 pairs as do the 10 base T and 100 base T standards, and it adds a pair at pins 4 and 5 and the final pair at pins 7 and 8, as shown in this picture. Whereas, the gigabit Ethernet crossover cable crosses the same 2 wire pairs 1,2 and 3,6 as the crossover cable for the other types of Ethernet, and it also crosses the 2 new pairs, as well the pair at pins 4, 5 with the pair at pin 7, 8. You should know that the capability of many UTP-based Ethernet standards is to use a cable length up to 100 meters. That means the distance from an Ethernet switch to every will likely be less than 100 meters. In some cases, an engineer might prefer to use fiber cabling for some links in an Ethernet LAN, to reach greater distances. So, this last section of the video, I will explain important things you should know about fiber for CCNA. Fiber optic cabling uses glass as the medium through which light passes. It might seem strange at first to use glass given that most of us think of glass in windows. Window glass is hard, and if you hit or bend it enough, the glass will probably shatter. Instead, fiber optic cables use flexible fiberglass. A fiber optic cable holds the fiber in the middle of the cable, allowing the light to pass through the glass. The glass could break, so the glass fiber needs some protection as shown in this picture. The 3 outer layers of the cable protect the interior of the cable, while the inner cladding and core work together to create the environment to allow transmission of light over the cable. A light source, called the optical transmitter, shines a light into the core. Light can pass through the core, however, light reflects off the cladding back into the core. The picture shows the normal operation of a multi-mode fiber, characterized by the fact that the cable allows for multiple angles of entering the core. In contrast, single-mode fiber uses a smaller diameter core, around 1/5 the diameter of common multi-mode cables. To transmit light into a much smaller core, a transmitter sends light at a single. Remember that the distance might be the first criterion to consider when thinking about whether to use UTP or fiber cabling. Both multi-mode and single-mode cabling improves the maximum distances over UTP. But, a few other trade-offs exist as well. For instance, the cost goes up as you move from UTP to multi-mode, and then to single-mode. UTP has some negatives, however. First, UTP can be affected by electromagnetic interference. This table summarizes these trade-offs. So, I hope that my explanation was clear. That's all you need to know for part 1. If you have any question, leave comments, I respond quickly. Now, I have put some questions to check if you understand correctly. Question 1. Which of the following Ethernet standards defines Gigabit Ethernet over UTP cabling? I give you few seconds to answer. Okay, the good answer is C, because the answer A 10BASE-T refers just Ethernet, and the answer B 100BASE-T is the fast Ethernet, whereas the answer C 1000BASE-T is the Gigabit Ethernet. Okay, like I said before, when I explained this table. Now, question 2. Which of the following is true about Ethernet crossover cables for fast Ethernet? I give you few seconds to find a good answer. The correct answer is B. The crossover cables for fast Ethernet, the pins 1 and 2 on one end of the cable connect to pins 3 and 6 on the other end of the cable. Like I explained before when I tried to explain connection between two switch, where both endpoints transmit on the same pin pair. You should remember that 10BASE-T and 100BASE-T use UTP cabling in similar ways. They use two pairs of wires in the UTP cable, one for each direction, but 1000BASE-T uses the 4 wire pairs. Okay? This is important for CCNA. This is all you need to know on part 1 for CCNA. I will soon publish a video of part 2, so subscribe and share the video with your friends, and don't forget like and leave comments because that will encourage me to publish other video. See you soon.